Okay, so we have a lot of conceptual questions for office hours. Oh, I bumped the camera. A lot of conceptual questions for office hours today. Talking about delta G versus delta G naught. We haven't technically gotten that into class yet, but if you're reading in the textbook, you've already started on that. Reactant favored versus product favored, which actually relates directly back to delta G. And then we can look at freezing point depression and colligative properties in the labs. All of these things, as we start to look at this, we start to realize all these things are actually connected to each other, right? It's really hard to separate them out from each other because all of them have to do with this idea of how much usable energy is there in a chemical reaction. I'm going to put superscript zeros on all of those. Right, so what does that superscript 0 mean? We call it naught, so this is delta G naught, delta H naught, delta S naught. And that, so far, this quarter is everything we've been doing. And this means standard conditions. Now, for us, standard conditions, I'll put standard in quotes, standard conditions only has two things associated with it so far. And this is why I haven't been real strict about this differentiation between the two. The standard conditions are temperature is equal to 25 degrees Celsius, which I apologize for this even though it's not my fault. Physics people used 0 degrees Celsius for their standard conditions, whereas chemists used 25 degrees Celsius for their standard conditions. So depending on where you're looking, standard temperature might be 0 or it might be 25. Physicists did it at 0 because it's numerically nice. Chemists did it at 25 because it's experimentally nice. Right? Most of our experiments are in a room where we are between 20 and 25 degrees Celsius. And usually in that 5 degrees C temperature range, these values don't shift that much. So we'll notice delta G, delta H, and delta S typically don't depend on temperature that much for the standard, right? Delta G obviously does, it has temperature in there. So our delta G tables are always at 25 degrees Celsius. Delta H and delta S, if we change the temperature 20, 30 degrees, we don't really see them change that much. So that doesn't really matter. The other thing is pressure is 1 atmosphere. Right, this is, again, a really standard chemist thing. 1 atmosphere is about the atmospheric pressure we're under right now. So it's really experimentally useful to set that as our standard conditions. Today it's cloudy. We've got a storm coming in. We've got a low pressure system. So maybe we're at 0.997 or 0.98 atmospheres today. Like our atmospheric pressure might be a little bit lower, but it's still about 1. And so that's a pretty good standard. The new thing that we're going to throw in, and this is for tomorrow, and this is where this is going to be important. This is new. We're going to have a standard concentration show up, where standard concentration is 1 molarity. The reason this becomes important, hasn't been important yet and is about to become important, is because so far we've really been talking just about thermodynamic equilibrium. Right? We've been talking about energy flowing back and forth. We've been talking about spontaneous or non-spontaneous in terms of energetic ideas. Tomorrow we're making a pretty big shift to start talking about chemical equilibrium. And again, I'm working on rewriting my lecture. Like this, normally when I teach 125, it feels like it's going really well. This quarter I've been like flustered because I've decided to rewrite a bunch of my lectures to try and streamline. Like I feel like I was looking at my past slides and I was like, this is kind of clunky. And I've been streamlining a bunch of things. I've been changing the way I'm talking about them to try and make it. And I've deleted a bunch of slides where I'm like, I don't need to do this like weird thing. And I'm doing that again for this. where I'm like, I hope I have lecture slides ready, but I might just be doing a whiteboard talk tomorrow for class. And then we'll do lab to experimentally explore it. As we switch from talking about thermodynamics and thermodynamic equilibrium to chemical equilibrium, we're going to shift from talking about joules per mole to talking about moles per liter, concentrations. And so that's where that standard condition is going to become really important. So delta G without the superscript, that's the Gibbs free. At non-standard conditions. Now, when we do these non-standard conditions, it's still usually 1 atmosphere. This will allow us to vary the temperature and change that temperature in the delta G equation to get it to non-standard. Most of the time we do this from now on, it's going to be non-standard concentrations. When we think about our biggest experimental variable in chemistry, like, sure, we can heat things up and cool them off, but when we're mixing things together in the lab, it's usually the concentration change that matters. So our delta G without the superscript, our non-standard, is going to be what happens if we mess with the concentration of our solutions. What if our solutions are not 1 molar concentration to begin with? How does that affect things? Which we have right now, unless you've been reading in the textbook and getting ahead of class, which I strongly recommend, we have no context of what it means for concentration to affect the Gibbs free energy. Just none. You do, but like most of us have none. Right? You do, but most of us have none until we like get through this next 2 weeks of class. So hasn't been that important yet for the difference between the superscript 0 being there and not being there. But it's going to become really important starting tomorrow. This gets also into the idea of spontaneous and non-spontaneous versus product favored versus reactant favored. When we talk about delta G superscript 0, I got to make sure I get this right. I got to check my lecture slides. That's where we talk about product favored or reactant favored from standard conditions versus being spontaneous or non-spontaneous from any condition. So they have 2 slightly different meanings, and we start to distinguish those meanings. Right? Up to now, I've said delta G can be spontaneous or non-spontaneous, product favored or reactant favored, and we've used those kind of interchangeably. But we're going to start to be a lot more careful with that when we start talking about delta G naught being product favored or reactant favored from standard conditions versus spontaneous or non-spontaneous, which is mostly in the physics world. Delta G can be at any concentration, whereas our delta G standard has to be at 1 molarity. Right, and then we can say how does, well, so standard conditions would be 1 molarity, and then our delta G would be the change from that standard to wherever it goes to get to energy equilibrium. And that's going to be kind of like new language we start dealing with tomorrow. So let's talk a little bit, okay, if I erase this and we talk more about product favored versus reactant favored? Okay. So let's look at a particular example and think about what this language means in product favored, reactant favored. Do you have an example in mind, or can I just pick something random?
It can be anything. I think because I haven't been thinking like of that, but thinking of it is it spontaneous or not? Like is it delta G negative or positive?
So yeah, and that's let's get that down first, right? So delta G greater than 0 is non-spontaneous. You'll notice I almost always put non-spontaneous and spontaneous in quotes. Hey, how's it going?
Yeah.
Office hours or something else?
I was just going to chat for a second. I've been gone for the last week and a half.
Okay, give me just a moment. Okay, so delta G non-spontaneous, but hang on, grab a chair. This might be useful as well.
Yeah, I don't want to see
Yeah.
what I'm...
Delta G equal to 0 would be kind of not changing, just static. And then delta G less than 0 would be spontaneous. And I've used some similar words for this, right? I've said this is product favored. Nope, sorry, lies. Got it backwards. This one's product favored. This one's reactant favored. This one's still equilibrium. And we can think about it a little bit better if we look at it at actual chemical reaction. So I'm going to go ahead and just pick one. Let's say we've got I didn't give myself enough space, but that's going to make sodium acetate aqueous. Right, so this is an acid-base reaction. And this acid-base reaction is going to be product favored. It's going to be spontaneous. I just know because I know this reaction, right? We'd have to have some other information to know otherwise. But I picked one that's particularly product favored. So what does it mean for it to be product favored with this context of concentrations? Well, that means if I started with 1.00 molarity here, 1.000 molarity here, and 1.00 molarity here, right? So standard conditions, we're not going to put a concentration for water. The reaction, if everything was at 1 molar solutions, the reaction would still go that direction, right? These concentrations would go down, this concentration would get bigger. Product favored.
What do you mean, like constant? Because like once you mix them together, are they not?
They're going to react.
Okay.
Right, so we're not just thinking like react, we're thinking about the process of reacting now. So, right, we can have something where I mix two things together and nothing happens.
Mm-hmm.
We can have something where I mix it, and notice I'm not just mixing the reactants together, I'm mixing all three of these things together at 1 molarity, right? Because I'm doing it from standard conditions. So I'm mixing all three things together, and when all three things are in there at 1 molarity, do we make more products or do we make more reactants?
So you're not, when you do the reaction, it's not just the first two you're mixing together?
When we think about this in terms of equilibrium and which way the reaction goes, we're really mixing all things together and saying, okay, what would happen if all things were there? Now, that's not how we normally do it, but that's how we conceptually think about it. Normally, this is 0. And if that's 0, of course, we've got to move that direction. We don't have context for what it means if that's 0, though, right? Because we haven't started learning about equilibrium yet. So, and this is the world we're getting into kind of tomorrow, right? So if I had standard conditions, all solutions would be at 1 molarity. All the products and all the reactants would be at 1 molarity, which is weird. But we can do that, right? I can go get a thing of sodium acetate, sodium hydroxide, and acetic acid. I can dump them all together. So they would all, at the second that they mix, if I could freeze time right there and say, okay, how's it look right when I mix them together? Everything would be 1 molarity. But I can't actually freeze time, so as soon as I mix them, it starts reacting. And we say, okay, well, which way is this reaction going to go? Is sodium acetate going to react with water and actually split apart the water? Or is acetic acid and sodium hydroxide going to react together to form more water? Now, I picked a problem where it's very much product favored. So eventually, if I left all of this sitting here, this would go to, at the end of the reaction, this would be approximately 0, this would be approximately 0, and this would be approximately, right, it's going to be -1, -1, +1. This would be approximately 2.00 molarity. Both of those things would be completely used up, making more water and making more sodium acetate. So I'd end up with...
Would it be -1?
-1 from the reactants, -1 from the reactants, +1 to the products.
I don't think I'm following.
Oh!
Like, where are you getting 2 from then?
Okay, so let's do this. Okay.
Because it's -2 + 1, right? Is that not -1? I'm sorry, I don't think I follow what you're saying.
So that's because we're getting into things we haven't done yet,
oh, okay.
right? So let's do it in terms of the stoichiometry. And let's just do stoichiometry rather than concentration. So if I've got...
Also, when you're saying that, like, you mix them all together, like, you're saying, like, when you're thinking about it theoretically, to think as if you're mixing, like, everything together to see what happens, but when you actually do it, you're just mixing, like, the reactants, no? Like, if we're doing this reaction, is it not just mixing the reactants?
Yeah, it is just mixing the reactants.
Is it like taking the moles of the reactants and just, they go to the moles as products?
Yeah.
And that change polarity?
That's how we do it experimentally usually, right? But in that situation, we could never have something that was like reactant favored, right? So essentially what we do, here's the way we think about it, as we start to get into this idea of equilibrium, is we set up, hey, come on in, grab a chair. Yeah, come on in, set your bags down, put them underneath things. So we essentially set up, I can't see them on the screen, okay. So we set up, like, essentially the chemical reaction is this teeter-totter that could go towards products or towards reactants. And we set it up so it's completely balanced, like we've got one weight, we've got like one reactant, one product. We set it up balanced, but when we let it go, it tips one direction to find its energetic balance. So we set up a chemical balance, and then it shifts to create an energetic balance.
Like when we do the reaction?
Yeah.
Or when we mix them together?
Yeah, so when we mix them,
finding the energetic balance.
yeah, so it finds that minimum energy of products and reactants. It shifts because remember, delta H is sum of products minus sum of reactants. So delta H has this idea of how much products is there, how much reactants is there. We calculate those in terms of moles of reaction to make it easier. We just look at the delta H for the overall reaction, but each product and each reactant puts in some amount of energy. And so we can think about this like, essentially what standard conditions does is set up the teeter-totter at some balance point where it's like same amount of products, same amount of reactants, and then it shifts. And we're seeing how it shifts. That's not how we do it in our laboratories. Someone can come take this chair if we scoop bags underneath things. If you're comfortable sitting on the floor, you can come on in. Right? In experiments, usually we have it so it's like all on the reactant side. It's recording. So just watch out. We have it so it's all on the reactant side, and it has to shift at least a little towards the product side. Even more so, where this gets weird for all of us, is at this point in our chemistry experience, and unless you're reading in the textbook and you had like a really great AP Chem class in high school, at this point in our chemistry experience, we've only done reactions like this one, where, because we know now that like really it should be going both directions, it can go either way. But all of the reactions we've done, including this one I have on the board, if I drew these arrows proportional to how much products, how much reactants, I would draw it like this, right? This arrow would be massive. That would be the backwards arrow, right? We do all of these reactions that just go to products. All of the energy balances if it makes a bunch of products. And we've never looked at a reaction that would have like this balance between the forward and the backwards, where it's like, no, actually when you mix these things together, you don't make 100% products. You only make like 60% products.
Is that like when like if something like not all of it dissolves, but some of it does? Like would that be?
That could be part of it. That's usually a saturation issue. Mm-hmm. This is more going to be the place where this gets interesting for me, which we're only going to barely talk about this quarter. What's your major again?
Civil.
So okay, well, you don't have to take Chem 129 then. We'll barely talk about it this quarter. It's this really important chemical mixture that exists in all biological systems. It's called a buffer. And a buffer is something that does not completely react. It has only a partial reaction, and that allows it to resist other reactions. So it can essentially keep your blood at a certain level, like in terms of the other chemical compounds that are there. And so it's really important in biological and environmental situations. Soil has to be pH balanced, water has, like a friend of mine, this is really silly, a friend of mine was like, who doesn't like chemistry, was like, I do a lot of chemistry now because I got a hot tub. Because you have to pH balance the water, you have to pay attention to how much solids dissolve in terms of the chemicals you're putting in, how much disinfectant you're putting in. You want to get it to the right concentration level to where it kills all the bacteria but doesn't cause skin issues for you. There's like all of these different chemical things you have to take care of. So if you don't care about the world, if you ever get a hot tub, you'll have to pH balance your water using buffers, using these chemical reactions that don't actually go all the way to completion. Like everything we saw in Chem 124 was just like all products. Our combustion reactions, all products, right? All of the things we've looked at to this point have always been all products. In truth, they've been 99.999999999% products. It's close enough that we say all products. This class, starting tomorrow, is going to be the first time we get to start looking at things where it's like, well, what if it doesn't go all the way? What if the delta H and the delta S makes it so it only partially reacts? And that's kind of like where we get to this weird idea of, well, so like, how big is I just erased it. How big is this little backwards arrow? And does it matter or not? In this reaction, it doesn't matter at all.
Wait, so when we say it's reactant favored, in the cases we've experienced before, it's when there is no reaction, right?
Yes. So right, when we've been saying it's reactant favored, it's like no reaction happening because we mix the two things and they don't react. They don't make any products. In truth, they might make 0.000000001% products, but nothing we've done has been sensitive enough to look at that.
Okay.
When we really start to this idea of reactant favored, what we mean is if I have a mixture of these three things, it would go back to, which is not this case, but if I had a mixture of these three things, it would go back towards reactants. And we'd have to look at, and we've never seen that before. So right, we've used this word reactant favored as a synonym for non-spontaneous. And tomorrow is the first place where we start to explore that idea of, well, what do we really mean by reactant favored? And that's the idea of I've got one molarity here, I've got one molarity here, I've got one molarity here, I've got a bunch of water. And now I actually have the option of these two things could react and go towards reactants and be reactant favored, or these two things could react and go that way and be product favored. Everything's there. Now which way does it, we've got that teeter-totter balanced. Now which way does it go? Everything we've looked at in our chemistry classes till now, till tomorrow, have always been like, oh, it just goes all the way this way. So we've never had to think about this before. And tomorrow we're actually going to start talking about, okay, we've got this teeter-totter balanced, but if it's reactant favored, it's like the person over here is a lot heavier and it's going to switch back. These things will react and actually make more reactants show up, which we haven't done before. So we can start to think about those things. But it takes a lot of work to get there. So these idea of reactant favored and product favored is I set up the teeter-totter, it's perfectly balanced. As long as I'm holding on to it, what happens when I let go?
So starting tomorrow, basically, reactant favored doesn't mean that like nothing happens. It means that like more reactants are being created when you mix them.
It means when we reach equilibrium, there's a higher concentration of reactants.
So it's only at equilibrium.
Yeah.
And that's relevant. But this still is relevant like when we're not at equilibrium.
Ooh, which this?
At the top, like how we said non-spontaneous is reactant favored.
Yeah.
So like, okay, so is this equilibrium like that equilibrium that's up there? Is it a different equilibrium that you're talking about?
In terms of delta G being 0?
Yeah.
that is equilibrium, right? So that is going to be the energetic point. The place where we haven't done this before, which is what's making it difficult, is we haven't done chemical equilibrium, where it's rather than changing like the energy of like Q in, Q out to get to equilibrium, we're actually going to change the chemical concentrations to get to equilibrium. So we can change like these 1 molarities. Nature by itself, without me doing anything, will shift these values to get to and stop at some point. And it'll stop when it gets to chemical equilibrium. I'm trying to think of an example that would work for talking about that.
So, like, does this have anything to do with something spontaneous or non-spontaneous, or is it separate from?
It's related. It's difficult. We won't get to the whole how they relate really until after the midterm. That's part of why I'm not getting into it yet.
Okay.
Because there's these really cool charts we can draw, but we gotta do a little bit more. We gotta read more in the textbook and have a little bit more time in class before it really starts to make sense. But essentially, non-spontaneous, spontaneous. So the reactant favored, I didn't give myself enough space for this, but reactant favored is really delta G naught is greater than 0. Delta G naught is equal to 0. Delta G naught is less than 0. Right? So it's the delta G can be from any point. We can just make up like whatever we want, whereas we're looking at standard conditions. So this blue part's in standard conditions, where we've got this new piece to our standard conditions of standard concentrations, which we've never talked about before. So it gets weird, and then it gets really easy. Right, this is going to be one of those things that is conceptually the step between these two things to getting to chemical equilibrium is like 4 weeks of an upper division class. And I'm going to be like, here's how we can do it in a quick way. And the quick way we're going to do it is we're going to define some equilibrium constant that's going to be concentration of products at equilibrium divided by concentration of reactants at equilibrium, where a bracket around something means concentration of. And we use this shorthand because we just write, we do so much stuff with concentration, and we want to like have a quicker notation for the fact that we're talking about concentration. This is, we're kind of getting ahead of where we are. But it's interesting to me. And I'm also kind of like, these questions are good because, like I said, I'm rewriting my lecture for tomorrow right now. And it's a little late for rewriting my lecture for tomorrow when I still have to finish writing your exams for Thursday. But I really want to rewrite it because it's clunky. It's weird. Lots of questions about this, I assume. But I'll tell you all here now, this idea of chemical equilibrium, the stuff that we're doing for like the second half of class tomorrow, will not be on the exam. So while I'm keen to keep talking about this and like get deep into it, it's probably best if we focus on some of the colligative properties stuff and the freezing point stuff. And any other specific questions we want to add to the list. Do you have a specific question?
I'm not in your class,
I know.
But I have to do the colligative lab.
Let's talk about the colligative properties. Can we talk about the colligative properties lab? Okay, so we're going to start talking about the colligative properties lab, and I'm going to start with just kind of going through the whole concept of what's happening with freezing point depression, why it's happening. I think this is a pretty cool idea. And here's essentially what's happening. We've got a liquid. It's got some number of particles in it. And when we freeze it, let's say we don't freeze the whole thing, we just freeze part of it. I got it in a sealed container. I don't know why I'm putting it in a sealed container. Like, one corner of it It's that really nicely ordered solid, right? So we've got some solid forming. We still have some liquid versus all liquid over here. Now, in this process, delta S has some positive value because we've got some entropy here, and then over here we've got less entropy. So we've got entropy, let's see, how can I do this? Over here we've got some entropy. Over here we've got, oh, did I say positive? That's negative. Whoops. Right, because we're as soon as I was drawing my S's. And over here, since we've got this solid that's got this decrease, the S over on this side is going to be a little bit smaller. Right, because some of my microstates have gone away. So my S ends up a little bit smaller. So when I do final minus initial, I end up with a decrease in entropy. That's usually what we see in the freezing process anyway, right? We lose some of our ability to rearrange things. Where the colligative properties come in is it says, hey, let's do that again, but now we're going to do it where I've got my liquid. Right, I'm going through this freezing process, but now I'm throwing extra chunks of stuff in there. As long as those extra chunks that are getting thrown in are non-volatile, non-reactive, they just kind of float around, my S here is going to be even bigger. Because I've got more ways I can rearrange things. I've got more microstates. Then I go through the freezing process. I make my solid over here. I got my liquid over here. Right? And our material that we're throwing in doesn't end up in the solid. Right? So when I look at the entropy change that's happening here, my delta S for this is going to be, make sure I get this right. S is smaller. My delta S is going to end up being even smaller.
Wait, sorry. I get like confused with like enthalpy and like entropy and stuff like so. Like
yeah.
Entropy is like, is it dealing with like the free energy, or is that's the G?
Kind of. G is free energy. So there's three big terms we talk about. Delta H is like the heating and cooling term. That's exothermic, endothermic, feels hot, feels cold. Get it from bond energies and stuff like that. S, entropy, and I don't know how your instructor talked about it. Entropy is this really weird idea that's conceptually difficult and experimentally difficult, is the way I put it. And what it is kind of like how many different ways can you arrange your molecules, arrange your energy.
Oh, okay, it's the arrangement.
Yeah. And there's essentially a cost for keeping things organized. And that's like, so entropy pretty much says we are not organized, but keeping things dense. Entropy pretty much causes this diffusion of energy, this distribution of energy. It spreads out the energy.
So when you add different things into the water, the overall change of the entropy is smaller than the overall change up there?
Yeah.
Meaning they're like more tightly compact, like the arrangement?
Let me think about this. And this is where I usually do it for boiling, so hang on a second. I got to make sure I get this right. So this S should be smaller. Right, because I've got this frozen bit that's going to be the same, but this has more microstates to it.
What's the orange again?
The oranges are our extra solute that we've thrown in, something that's non-volatile, non-reactive. Hang on a second. I have to do it for gases real quick. I have an easier time thinking about it for gases. So this is going to be S, really big S. Okay. Okay, so when I subtract these two, I get something that's positive. When I subtract these two, I get something that's a bigger positive, which means okay. I think I've got it. I think I'm right. It's a smaller negative, right? Because when I subtract these two, yep. Okay, cool. I do have it right. So essentially, because we get this, like, you know, since when liquids freeze, they typically exclude the solute, unless we're really careful about it. This is like, you ever have those popsicles and all the sugar's like sunk to the bottom of the popsicle? Right, where it's like all gooey on the bottom and like the top is like less flavorful, less sweet. That's because as the water is freezing, essentially the ice crystals, unless you're freezing it really fast so that the materials get trapped in, as water freezes, it would rather just freeze with itself, and it'll push that other material out. So we end up with like a chunk of ice at the bottom that's just water molecules, and we end up with our rest of solution freezing. And so in this situation, we end up with kind of a smaller change in entropy as we go from one to the other. Now, what does that mean for us? What that means is when I start looking at my delta G equals delta H minus T delta S, the temperature at which this is going to hit the balance, where this is going to hit equilibrium, where this process is going to happen, that temperature changes. Right? And so
the
this
delta H and the delta G don't change with that, right?
The delta H doesn't change.
Yeah.
The delta G kind of changes, but we're going to change the temperature to get it back to where we want it to be. So, for example, if we mix these things together, like this solution is going to have a different delta G than that solution. But if we're forcing them to freeze, this solution, the delta G at which freezing is going to happen, is going to be, or the temperature at which, you know, this process becomes spontaneous, this delta G switches to be equal to 0. The temperature at which this process happens is going to be different than the temperature at which this process happens, because we are affecting this delta S. And so what we're looking for in that is we're looking for this case, we're looking for the case where delta G equals 0, the spot where it switches from spontaneous to non-spontaneous. My example I used in class was water does not freeze at room temperature, right? So we turn down the temperature because delta G is not spontaneous at 25 degrees Celsius. So I start turning down the temperature until it becomes spontaneous when it switches from being positive to being negative. And I'm affecting the temperature to make that happen. So I'm looking for this place where delta H equals T delta S. Adding that over here, I'll write it the other way because people like it this way better. When delta G is equal to 0, I can add this over and I can have T delta S is equal to delta H. That's going to be the spot at which it switches from being spontaneous to non-spontaneous. I'm using that language because we're not doing chemical equilibrium yet. So again, for freezing, this makes sense for us. Water doesn't freeze at room temperature, but if I could crank the room down to 0 degrees, the water just starts to freeze in the room without me having to do anything else to it. However, if I put stuff in it and I change this delta S, the temperature at which that happens also changes.
So for freezing, if you change the delta S, since the delta S is getting smaller with the stuff in it, when the temperature have to get bigger?
Did I flip my signs? Hey, come in and grab a chair. Let me make sure I'm thinking about this right. Delta S would be negative, so if delta S Kelvin, entropy is having, if entropy is smaller.
But wouldn't it be a larger negative number?
For the temperature?
Yeah.
Yes, and that's where we have to be careful. Right, so the situation where this is going to happen, right, we need to put it into Kelvin. And so I think it's going to be, like the delta T is what we need to look at. So we'd see this happening, that it would be a larger negative delta T, so that's essentially going to be like the change in temperature is going to be lower. Right, so it depends on whether we're looking at temperature or delta T. If we're just looking at temperature, we would need to get the actual sign of delta H and delta S to figure this out. We have situations, there are certain compounds that will never become spontaneous. Delta G is always positive. And we've got certain situations that are never non-spontaneous. Delta G is always negative. We're looking for these situations where the delta H and the delta S are, I think it's usually opposite signs. So if this delta H is negative, or is it the same sign? It's when they're the same signs, right? I want my delta H to be negative and my delta S to be negative, because then it's the double negative makes it positive so I can affect it. So when delta H and the delta S are the same sign, we can have these temperature effects come in. So for the freezing process, freezing is exothermic, the delta H is negative, I'm going to divide by the delta S, and that's going to make, maybe you're right, maybe it is a bigger negative. The point is, entropy can affect it.
So like when we did the ice, the thing we did in like the lab in class, what were we affected the delta S, right? By putting salt in it.
Exactly.
And then
we saw the freezing point change.
Yeah, but didn't the freezing point get lower?
It did. Which is where I'm like, I might have this part wrong. I'm pretty sure I have it right. The temperature got lower. So if I think about this, the change in delta S is a smaller negative number versus a bigger negative number. Dividing by it, temperature is going to be higher. My analogy might be flawed.
Be delta H plus T delta S then, because the delta S is negative?
If we brought the negative out, but without knowing the sign of it, we would just have this condition.
Yeah.
And we might find that we end up with like impossible temperatures. And still, the most important thing here is we can see that there's some entropic effect that's going to affect the temperature at which it freezes. That's the important thing. That's the important thing. Like I said, I usually do this better with like boiling thinking rather than freezing thinking. So the important part here is that entropy, affecting the entropy of the solution, can affect the freezing point. Okay. And the interesting thing about it is it doesn't matter what those orange dots are. Just the fact that the orange dots are there means that we're going to have some effect on the entropy.
But weren't we not freezing the water inside the actual like solution mixture? We were freezing something that wasn't actually in it.
It was mostly water.
But like we weren't, like in your diagram here, you froze something in the like water and salt or whatever the thing, and then we stuck something else in it, and that's what froze.
Wait, what?
Like we took the test tubes of the thing that was freezing, right? And we put it in our mixture to freeze.
This would be the test tube.
Oh.
This would be the test tube.
Okay.
These would be the test tubes, not the bath that we made.
Okay, that makes sense.
This is the test tube. Sorry. Yeah.
Okay, that makes sense.
Okay. Sorry. Let's talk about, so again, back to the important part. It's just, it doesn't matter what those orange dots are, just as long as they're there, because this is an entropic effect. So what that means is when we start thinking about this, as long as it's not reacting, we end up with this situation where I just care about how many dots are there. And so to figure that out, we use two different variables. We use this idea of molality, which is going to be moles of solute per kilogram of solvent. Slight switch from our idea of molarity because we don't want to use volume because volume changes with temperature. And then we also use this idea of I, which is called the Van Hoff factor. And then the Van Hoff factor is there to take into account that sometimes we've got a certain moles of solute, but then that solute dissolves in water and changes when we put it into water. It's not really reacting with the water, but it's putting more things into the water than we're expecting. And so we say, okay, well, where are places where we can know what's going on with the Van Hoff factor? The easiest is covalent compounds. Covalent compounds shouldn't break apart in water. Covalent bonds, besides strong acid bonds, which are kind of a weird case, covalent bonds don't break apart in water. So covalent compounds would end up having a Van Hoff factor. If I put one covalent molecule in, it's just one thing. So in that situation, my ideal Van Hoff factor, ideal or theoretical for a covalent compound, would just be 1. Right? I have one molecule, I put that one molecule into water, it doesn't break apart into other little chunks, so it's just one orange dot. The place where it gets a little tricky is when we start looking at ionic compounds. Right? If I look at something like sodium chloride, sodium chloride is something that's a plus cation and a minus anion. In that situation, when I put sodium chloride into water, it's not putting one thing, it's actually putting 2 things into the water. Because the Na plus and the Cl minus are going to split away from each other. So in the picture that I erased, one molecule of sodium chloride would actually be 2 orange dots. Right? One molecule of sodium chloride, right? It's like I put one pen in, but one pen is actually a cap and a pen. And so it's actually 2 pieces of things when it's in water. So the ideal Van Hoff factor takes into account the fact that you thought you were just putting sodium chloride in there, but you're putting sodium ions and chloride ions. And because this is an entropy effect, right, that would mess with the delta H in all kinds of weird ways. That's the lattice energy versus the hydration energy. But because we're looking at the entropy effect, all we care about is the number of things that end up there. So we end up with 2 things there. Van Hoff factor takes that into account. But we can have other ionic compounds. Right, another example, I'll use one from lab. Right, magnesium chloride, really important that we recognize that this is not magnesium chlorine gas or some weird thing like this. This is magnesium chloride. So it's going to be a +2 charge with 2 Cl minuses attracted to it. So when I put this thing into water, how many objects am I actually putting into the water? Show me with your fingers. I'm actually putting the minus, the plus, and the minus. I'm actually putting 3 things into the water. And again, you might be like, well, aren't 2 of them Cl minus? But it's like, no, all that matters is how many objects are going into the water. I thought I was putting too many things. I thought I was putting 1 magnesium chloride into water. Right? Here's my magnesium chloride. The magnesium chloride is actually 3 different things going into the water. So when I start thinking about the entropy, I've got to take into account that there's 3 objects that are going to affect the entropy, the number of microstates, the number of ways that all my molecules can rearrange. So that's going to affect the entropy in ways that I might not have expected. So that's the ideal Van Hoff factor. You just look at how many ions there are.
So when you're like doing a question where you're solving for something, do you use the ideal Van Hoff factor?
Almost always.
Unless it asks you to solve for
Right.
it?
In this lab, we had a compound where it was like, hey, calculate the experimental Van Hoff factor.
Mm-hmm.
We know it should be, I think magnesium, I had some students get really weird numbers with magnesium chloride. We were like, we know it should be 3, and we know it can't be bigger than 3. Right? Because a Van Hoff factor has the maximum number of things that can fall apart, right? It falls apart into 3 things. Can magnesium chloride ever fall apart into more than 3 things? No. So, could it fall apart into less than 3 things? Well, it could be that like one of the chlorines doesn't fall off completely. They stay next to each other too much. It could be the way that the water molecules are rearranging around the ions. Maybe the entropy is not increasing as much as we think it is because of that ion-dipole interaction. There are things that can make the Van Hoff factor slightly less than 3, but there's nothing that can really make it more than 3.
Wait, so what's the difference between theoretical and experimental?
So the experimental can be lower than we think, right? Theoretical is just like, I'm looking at paper, magnesium chloride should be 3. Experimental, we actually do an experiment, we collect data, and we say, what did the Van Hoff factor for magnesium chloride, what do we actually get? Does it affect the entropy in this like 3 things end up in solution way, or is it a little weaker than 3? Is it like 2.9, 2.8? The ideal Van Hoff factors, the theoretical ones, are always whole numbers. They're 1, 2, 3, 4, 5, 6. Well, I can't think of anything that would actually, I mean, there's some things that could do 6, but that'd be weird. Right, they're whole numbers. The experimental Van Hoff factor could be something a little bit lower. Right, you could end up with, in water, the magnesium chloride, maybe one chlorine falls off really easily and the other one doesn't, so it ends up being 2. Or maybe this one like falls off for some of the time, but then pops back on for some of the time. It falls off for some of the time. That would make it like 2.5. But it's not falling off all of the time. And so we can have these kind of experimental things that we could, through careful consideration of thermodynamics and activity coefficients, take into account. But that's like an upper division chemistry class in thermodynamics. We're not going to do that. So we just say, look, it's either the ideal number or it's something we do an experiment to figure out. Hopefully, we do an experiment and our experiment just gets the ideal number. That's what should happen, because then our theory matches with our experimentation. And if our if our theory does not match with our experimentation, we don't go, oh, experiment wrong. It means fixed theory. And that's where we have this, like, how could the Van Hoff factor be less than 3 for something like magnesium chloride? And it's just the ions are interacting with each other to some degree, where we assume that they're, like, this assumes the ions don't interact with each other at all. That you have plus ions in solution, you have minus ions in solution, and they don't interact with each other at all. But if you have plus charges and minus charges, could they interact some? They could. Could you have water getting in the way of that? Yeah. Could water getting in the way affect that change in entropy idea for the ions in solution? It could, and it would lower it, and it would make the Van Hoff factor seem a little bit lower. Yeah.
In the lab, our experimental factor was higher.
Yeah.
So
that's where I said I had a student. I don't think it was you. I had a student. Let's do a calculation. Can we do it? Who's got data they want to do a calculation for experimental Van Hoff factor?
I got mine is like 12.
Okay, let's go ahead and do a calculation for experimental Van Hoff factor. Let's do it with somebody who's got this bad data. Let's talk about like what might be going on there. Okay, and then we'll do question 3. So there's 2 equations there's kind of 3 steps to doing this experiment. The first is, I'm going to switch colors again to, yeah, there we go. So our temperature of freezing for the solution is going to be equal to our temperature of freezing for the solvent, in our case water, minus the delta T of F. Right, this is going to be, it's always minus because we know it's freezing point depression from the way that the entropy affects it, even though I might have had my pictures a little bit wrong last time. Boiling point's always greater, freezing point's always lower. You know, it was supposed to be a bigger minus. It's a bigger plus and a bigger minus. I did mess that up. You're right. Messed up my earlier picture. Sorry, people who watched that part of the video.
Wait, so the delta S would have been a bigger minus?
It would have been a bigger minus. I'm pretty sure, because in the boiling point you get a bigger plus, in the freezing point you get a bigger minus. and both make the changes bigger.
I have the data if you want.
Okay, almost there.
Okay.
The other thing we have to recognize is that this delta T of F is something we can calculate. It's equal to I KF times molality. Molality is something that we can calculate. Molality is going to be our x grams per gram, the weird units we use on the bottles, times 1,000 grams per kilogram, times 1 over molecular weight. Right, and that will get us to molarity from this being on the bottle. Solution, solvent, nothing with the solute here. Right, the solute is just there. It's some number, it's some concentration. Right, so it's in the I and the M. I should do this. This is solvent. This is solute. This is molecular weight of solute. Right, so we have to keep track of all of our different things. This would be 100 grams, 1,000 grams of solvent, kilograms of solvent. Because we want to get to that unit of kilograms of solvent, moles of solute. So we can put all these together. I have a bit of a math brain, so I tend to put my equations together. Now, for most of us, when we're doing water, this TF should just be 0, because water freezes at 0. Depending on your experiment, maybe this was a little bit bigger, a little bit smaller. That's our correction. And then we subtract that over. That's going to get us our delta TF. Making sure that if this is a negative and that's a negative, we get rid of our negatives. So let's go ahead. Let's take a look at your data. Just tell me what your data is. We'll do a calculation.
So we had dextrose, so the ideal one was 1.
Okay.
The mass of solute dissolved.
Were we solving for the Van Hoff factor in this? Which part are we looking at? Solving for the Van Hoff factor. Okay.
I think so, yeah.
Okay, let's do it.
So the mass of the solute dissolved was 0.1802 grams per
1 gram.
Yeah.
I know it's weird to have grams per gram, but it's grams per gram.
And then
Carefully saying this is solute and this is solvent.
okay. And then the corrected freezing point of water or of the thing was -2.2 degrees Celsius.
Okay, so that's going to end up being our, what was the corrected freezing point was 2.2? So that's already going to be those two, that's already going to be our delta T. So this is going to be equal to 2.2. I forgot to give space for my KF. Give me just 1 sec. But it's going to be like a negative of a negative, so you get rid of that.
What is the 1/8 that?
That's the number from the bottle for dextrose.
But then what is that giving you? Is that giving you the
That's going to
molality?
get us, yeah, so that's going to be this part here.
Okay.
This grams per gram is how it's given on the bottle. So I'm going to have my I. The KF for water, if I remember correctly, is 1.86. And it's like degrees Celsius per molality.
Yeah.
Per molal, that's how we say it. Kind of weird. And then I'm going to need the molecular weight. Of dextrose.
Um, 180.16 grams per mole.
About 180.2 grams per mole. Okay, so notice, once I plug in all my numbers...
Oh, wait, that was for glucose.
Oh, no, that's not good.
Hold on. Why is it showing me the wrong one? Hold on. I have it in my notes.
Okay.
Sorry.
Right, so whatever the case, notice right? These three green equations, how the freezing point is changing, the definition for our colligative property of delta T, and then how we deal with the unit conversions for molality. That's going to give us this kind of like overall equation where I essentially have three different things I might need to figure out. I could figure out the molecular weight, I could figure out the freezing point, I could figure out the Van Hoff factor. And each part of this lab just kind of switches, what are we solving for? Which thing do we know, which thing don't we know? And it just switches which variable we're solving for. It always gives us everything besides the one thing we're solving for. Did you find it?
So it is 180.
Okay. 180.2 grams. Perfect. Okay. So we've got all of our numbers. Now we just solve for I. And we should get something slightly lower than 1. We shouldn't get anything bigger than 1. We'll see how it goes. 2.2 divided by 1.86 divided by 0.1802 divided by 1,000 times 180.2. I got 1.18. Is that what you got?
I got 1.13. But
Okay.
yeah.
Maybe some rounding errors.
Yeah.
I got 1.183 for my Van Hoff factor. No units on it, right? Because it's supposed to be a counting number. I had students that got 12. Did you get 12?
Yeah, I got like, yeah.
Yeah, so I had some students that got like 12 for magnesium chloride. I had some students that got like 8 for sodium chloride. Like I had people getting numbers all over the place. And so we look at this and we say, okay, how could dextrose possibly give us more things in solution than it could? The answer is probably contamination, right? How do we get more things in solution than we thought possible? There's something besides dextrose, right? If it was only dextrose, I has to be 1 or lower. But if there's other things in there, if you didn't clean your glassware and somebody had some gunk in there, if you used, I had a group that was using their DI bottle at their table. Normally, in a lot of our experiments, tap water, DI water doesn't matter. This experiment, somebody filled up their DI bottle with tap water. And tap water has a bunch of ions and other stuff in it. Doesn't usually matter to us in a lot of our experiments. There's a few experiments where that difference between DI and tap makes a really big deal. This is one of them. In the future, when you're doing like a quant class, it always matters. Always matters. And so we want to be in the practice of always using DI water. But because I knew that DI water is a problem and not everyone fills those DI bottles in the Gen Chem class properly, I was just like, dump your bottle, fill it again. They're like, we used it twice, we got the same thing twice. I was like, dump it, refill it from the proper tap. They got totally different answers. So maybe you were using your DI bottle that you didn't fill up. You trusted somebody else in the class to fill it properly. It has a bunch of sodium and chlorides and magnesium. It has a bunch of extra junk in it that we didn't expect. That throws off your numbers. So all of the things that might be there that we didn't take into account. A change this small, I'm guessing dirty glassware, or like if you used the same stir stick and you kind of moved it between solutions, just put a little bit of extra stuff in there so you get a number that's a little bit high. When I see things like 12, I'm like, tap water, my first guess. Even if you use your DI bottle, if you didn't get it from the tap. Also, in the past, we've had, this was after the pandemic, like the first quarter after the pandemic, our DI system was actually not working properly and dumping a bunch of stuff into the DI water. It took us like 2 months to figure out what was going on. We had a tank. We used this like passive tank system for cleaning out the ions. And one of the tanks broke over the pandemic without us realizing it. It took us 2 months to figure out like why the DI water was like making reactions behave weird. Unusual. We usually monitor that. Could be that, but something happened. Dirty glassware, dirty DI water, dirty stir sticks, put some contamination in there. We've got things. In all of our consideration, we were only looking for dextrose. But what if there was something else there? Then it would look like our Van Hoff factor was bigger. In an ideal world, we would just go do the experiment again. We'd have the time to clean everything, clean the glassware, put it into an oven to dry it overnight before we go try to use it. You guys do this, don't you? Right? Put it into an oven to dry it overnight to make sure there's no water stuck inside of it. There's nothing there, no soap molecules left over. Because even soap will affect the freezing point and boiling point. It's a covalent compound that'll have some impact on the entropy of the solution. Soap will change when things freeze. So if you had soap residue in there, you're it's contamination someplace. And we redo the experiment, really, really careful. Everything being as pure as possible. We'd even test our DI water beforehand to make sure it has no ions on it. Then we'd be okay. Then we should see a Van Hoff factor that's reasonably lower than our theoretical, and not 12. Fortunately, with the labs that we're doing for our first year of chemistry, we're not really stressed about did you do the experiment perfect or not? We're interested in seeing that change in freezing point, that manipulation of the materials, that manipulation of the data, where you've done everything correctly. And you can look at it and say, my data doesn't make sense. I should do the experiment again, but we are moving on. Being able to have that analysis is the part that we're working on now. Should we do another problem? Question number 3. And then also, I don't remember your name. Did that help out?
Yeah, I did.
Okay, cool. Let's try number 3. This is the post-lab questions?
Yeah.
Cool. I'm going to erase all of this. No, I'll erase it all. I think those green equations will come in handy again. But we'll just rewrite them if we need to.
We can also do a different post-lab question if people have a different one.
That's okay. Let's do 3. We can do 3 and then do something else. What time is it?
It's 4:30.
Oh yeah, we got time to do 3 and 4 and 5 if we want.
What is the freezing point of a solution of 8 grams of blah blah blah?
Well, I need to know the blah blah blah.
Okay, well, she was just asking what the...
Yeah.
Oh, that it was the same number 3?
Yeah, mine's 8 question.
Okay, cool.
Okay, what is the freezing point of a solution of 8 grams of carbon tetrachloride, CCl4, and 50 grams of benzene? For benzene, T final equals 5.5 degrees Celsius, and K equals...
That's T freezing, not T
Or
final.
T freezing, sorry.
That's okay. We did a bunch of T final, T initial stuff, so.
And K of freezing equals 5.12 degrees kilograms moles to the -1.
I'm just going
I don't
to
know
do
why.
degrees.
Yeah,
They expanded the unit of molality, where
Okay.
my M looks really weird. I don't know what happened there. There we go. They just expanded the unit of molality. But I'm just going to put it in degrees Celsius per molal.
For the midterm, what things should we already know? Not content, but for example, polyatomic ions. And,
Oh yeah, all that stuff from 124.
the only thing that I have is polyatomic ions. That's the only thing
Polyatomic
I've
ions,
memorized.
periodic trends,
Oh, yeah.
carbonic versus covalent,
It comes back. It all comes back.
stoichiometry, all that stuff we did in
But
the first week
should we
of
know
these.
I don't know I don't remember what the
C6H6 and CCl4?
Yeah, I don't remember those
no,
names or
I just
something
know
like
those.
that. Oh, okay.
I would give those to you on an exam.
Okay.
You were never asked to remember. Carbon tetrachloride, kind of in nomenclature, but I would give those to you.
Alright.
Okay, so we've got our initial freezing point, we've got our freezing point constant, we've got the carbon tet in, and it's asking for the new freezing point?
Yeah.
I'm going to call this TF pure, and then we want to find TF solution. That's the thing we're looking for. Okay, so we're going to put 8 grams of carbon tet into 50 grams of benzene. It's a covalent compound, it's a nonpolar covalent compound, so it'll dissolve well in benzene. And we're going to see how the freezing point of benzene changes. This is a kind of fun problem because everything we did in lab was just looking at the freezing point of water and how that changes. But we can do this to any chemical compound. It doesn't have to just be water. This happens with anything that's going through a phase change. We see this freezing point depression, this boiling point elevation effect. So I'm going to go ahead, rather than calculate, does it ask for a final solution or the delta T?
Just says freezing point of solution.
Okay, well I'm going to calculate delta T first. My delta T of freezing is going to be I KF molality. Show me with fingers. What's the Van Hoff factor for carbon tetrachloride? It says carbon tetrachloride, but it's covalent. Do covalent compounds break apart?
No.
Nope. Ideal Van Hoff factor should be 1. My KF is going to be 5.12. My molality, I got to calculate my molality. Let's do a little side calculation real quick for molality. I got 8 grams carbon tetrachloride. I got 50 grams benzene. I'm going to go ahead and do that division to get it into grams per gram. I'm going to do 8 divided by 50. Whoop, that's not right. 8 divided by 50. That's going to get me 0.16 grams CCl4 per 1 gram C6 benzene, C6H6. And now I'm set up so I can do that same type of manipulation. I can multiply by 1,000 grams C6H6 per 1 kilogram C6H6. That will get me, I should be able to do that in my head, but 160 grams CCl4 per 1 kilogram C6H6. Is that still on the screen? Yeah, it's still on there. Okay. And now I've got to get, I don't want grams per kilogram, I want moles per kilogram. So I have to multiply by 1 mole CCl4. Now I need the molecular weight of carbon tetrachloride. That's going to be 140, chlorine is 35, so it's going to be 35 times 4, which I can't do in my head, but 35 times 2 is 70, so it's going to be 140, plus carbon is 12, 140 plus 152. Thumbs up if you agree. I'm kidding, let's just go with it.
153.81.
I rounded a bit on the chlorine. Let's go, 153.81.
Yeah.
Looked up or calculated?
Looked up.
I'm going to go with 152. Let me check something. So the discrepancy is the fact that chlorine is 35.45, not 35. Let's go with your number, it's more accurate. 153.8, because it should be, I did 35 because that's easier in my head. 53.8 grams. So I do 160 divided by 153.8, and that's going to get me 1.04. And I'm going to give it a little script M. It's going to be 1.04 molals. I plug that in here. That's going to get me my delta T. It's going to be about 5 degrees. Right? Because it's 1 and about 1, 5.12. Depending on your problem, you might have different randomized numbers, so don't just try to plug this final answer in. Check your numbers. The numbers are randomized. So we're going to do 1.04 times 5.12 times 1, and we're going to get delta T is equal to 5.33 degrees Celsius. Now, for my TF solution, I'm going to switch colors again for this part of the calculation. My TF solution is going to be the 5.5 pure minus the 5.33. From here, this 5.33 goes there, this 5.5 goes there. Right? I want to do my pure minus my delta T. Negative plus 5.5. I'm going to get 0.174 Celsius. Little rounding errors, but that should be about correct. So.
I got 0.18 and it kept saying it was wrong.
Oh, really?
Yeah, but now my Wi-Fi's not working, so I can't.
We can double check. So, but you were getting like 0.18
Yeah.
instead of 0.17?
Yeah. But I can't check if 0.17's right because my Wi-Fi's not.
I can check for you in just a sec. But this is the process. I feel like it should have accepted 0.18. Let me just check something real quick. Oops, I did something wrong there. Oh, I totally messed up that problem. 0.05 times 5.12. I'm just checking something real quick. 5.39. Yeah, I think you're 0.18. So I'll have to double check. Usually I allow for a 5% error in the question, so 1.7 versus 1.8 should be acceptable. This one I might have a tighter allowance, and so it might be like you need to get it really close to the right answer, because there is an exact answer here. The thing I was checking was if you messed up your molecular weight here like I almost did, it actually has a bigger effect than I thought it would. It takes it from 1.17 down to like 0.14. I wasn't expecting it to affect it that much, unless I punched it into my calculator quickly wrong, which is totally possible. Yeah, instead of getting 5.33, I get 5.39. Much bigger effect than like that little molecular weight change actually affected it more than I thought. Did it work?
Well, the lab's
Still no
disabled now. So
oh, I'll check it. And if it's right, we'll take care of it. So that's number 3 for us, number 8 for you. Other questions? Do we want to do another one?
I had a question from the quiz from us.
Sure. Before we switch to quiz questions, which we can totally do, other questions about colligative properties? Yeah.
No, not colligative properties.
Cool, then let's shift gears.
This was like.
So, hold that thought. Let me read this. We're going to do a quiz question, and then what was your question?
I just had a question on like the entropy trends from where the MQs.
Okay.
Like, you have to choose the salt that would have like
That was
the most positive delta S or something.
Let's do the quiz question first, and then we'll do the other one. Okay. So let's go ahead. Quiz 3, number
4. So it's a process increases the entropy of the system by 103 joules per mole Kelvin and absorbs 42 kilojoules per mole of heat from the surroundings. Does this process favor
how much heat?
42 kilojoules of mole or per mole of heat from the surroundings. Does this process favor products at high temperatures, low temperatures, and then at which temperature does it switch?
And it was, what was the delta S? The delta S was positive or negative? I missed that detail. It's important.
The process increases the entropy.
Increases, that's positive. And it absorbs from the
42
surroundings.
kilojoules
So it's also endothermic. So I like to put, again, I know it's silly to put positive on numbers, but with this material where that sign flip matters so much, I like to put the explicit positive. So it's like, I didn't forget a negative sign. Positive sign is there on purpose. Okay, so what we're going to have is we're going to see delta G equals delta H minus T delta S. And it's going to be, I'm going to go ahead and put it in, right now, this is 42 kilojoules per mole versus 103 joules. So this is like 42000 minus T times 103. If temperature goes low, and here's how I usually think about it. I think about like if temperature was close to 0. If temperature were close to 0, this thing would completely disappear. And then our delta G would have to be positive because delta H is positive. So non-spontaneous would never happen. However, if the temperature got really big, and it would have to get really big, right? Since these are off, like since this is 42,000 versus 100, I would need the temperature to be up around, what's 42 divided by 100? I would need the temperature to be up around 420 Kelvin. Right, so I'm doing 420 times 103. That's the only way I'm going to get that temperature. That's the only way that this negative thing is going to be big enough to overcome that 42,000. So I need a really big temperature. I think I did that right in my head. Maybe it's only...
Yeah, it's high.
Okay, it's high. So it needs to be a really big temperature. It can't be a low temperature. Is there a second part?
Oh yeah, and it's to find the temperature.
At which it switches?
Yeah, in Kelvin, yeah.
What's the temperature at which it switches? What's delta G when it switches from positive to negative? So we're going to do delta G equals 0. So delta G equals 0. I can rearrange. I can get T times 103 is equal to 42,000, sorry. And then I can just solve for T. It's just going to be 42,000 divided by 103. Uh, 407.76.
That was off.
What'd you get?
I think I did 4,200 instead of 42,000 because I had 40 point.
Yeah, you were off by a 0.
Yeah.
That's rough. Yeah, so you did everything correct, but you got that unit conversion wrong.
Yeah.
Or something, I don't know. And then...
Yeah, here, I'll just show you the question.
Okay, which one am I looking at?
23 or 24.
Okay, 23. Consider all the salts that could be made by using, what is this sentence even saying?
Yeah.
Combining, choosing. There's an extra word there. Made by combining, making, using, combining, choosing. Oh, I know what's happening.
Wait, what question? 3.1 question?
Yeah, just the last.
So I want to check the background code that's running this. My guess is there's supposed to be one of those 3 words chosen at random. So something that we did during the pandemic, which we stopped doing, was we would change different adjectives and verbs in the problems to make it so the problems had essentially fingerprints unique to each student. So if students tried to post them online for getting help, we could tell which student was posting them. And we caught a lot of people cheating that way.
Oh, wow.
So my guess is this was supposed to choose one of those 3 words, and then there's probably some other words, like depending on the different things that are getting selected, that would make it so there's something like 300 different ways that this one problem could be worded. And then we could tell within, if we've got a class of 300 students or less, we could tell exactly who had that random selection. In any case, consider all the salts that could be made by, I'm going to go with combining the cations from the list: barium, calcium, lithium, magnesium, potassium, cesium, sodium, strontium. We probably also randomized some of those things on the list, so it wasn't the same list for everybody. And the anions from the list: bromide, chloride, fluoride, oxide, and sulfide. Which of these salts would most likely to have a positive value for the delta S solution? Enter the name of the salt in the box. Bum, bum, bum. This is very similar, but not exactly the same as the delta H arguments. So let me write this down. Which homework is this, or which assignment is this?
It's 3.1, number 23.
So we're looking at 3.1, number 23? Okay. So here's what we have to think about. We're looking at delta S. So our delta S of solution, just like our delta H of solution, is going to be made by a delta S of lattice plus a delta S of hydration. The delta S of lattice is always positive, because we always increase our number of microstates when we break apart a solid. Our delta S of hydration is always negative, because we always decrease our microstates when we surround a molecule with an ion with water molecules. Now, when we were doing this with with delta H's, charge density would send the lattice up and the hydration down, so it would get more positive and more negative. Something different happens with entropy. That makes it so, and with our enthalpy, we couldn't predict anything. We were like, oh, we know it's going to become a bigger positive and bigger negative, but we don't know how fast each one's going. For our delta S, as charge density goes up, switch colors. As charge density increases, as charge density goes up, I'm going to do the magnitude of delta S of hydration goes up, right? It's going to become a bigger negative because as you increase that charge density, more and more water molecules can pack around it, right? This means more water molecules. The scientific way we would say this is we would end up with a larger solvation shell, more water molecules kind of packing around it, more water molecules sticking to it. More water molecules sticking to it would mean bigger decrease in entropy, less ways that those things can tumble around, decrease microstates. Same thing we saw with delta H of hydration. The place where it's different is the delta S of lattice. Now, we've got our crystalline solid. Let's say it's 1,000 ions. We break the 1,000 ions up. Does it matter if they're plus 2s and minus 2s? Still 1,000 ions. Charge density has no effect on the lattice entropy. Charge density ends up having no effect on the lattice lattice entropy. Because when we're looking at this lattice idea, the delta S of the lattice is just the delta S of the lattice, right? If I've got 1,000 ions that are all stuck in a rigid structure, and then I've got 1,000 ions that can all tumble around, it doesn't matter if they're plus 1s or plus 2s or plus 4s or plus 6s. It's just rigid versus tumbling. However, with the delta H, the enthalpy, plus 2s are harder to break apart than plus 1s, right? That charge had a direct effect on how much energy it took to break it apart. So for for enthalpy, we saw charge density affect the lattice. For entropy, charge density has no effect on the lattice. So we can see directly bigger charge densities are going to have a smaller delta S because we're going to have that bigger negative. And smaller charge densities are going to have a bigger delta S because they're going to have that smaller negative. Now, the question asks for something specific. Does it ask for...
It asks for what, like, combination of the cation and anions would be most likely to have a positive value for...
So, most likely to have a positive value of delta S, and I think number 24 is most likely to have a negative value of delta S. So if we want the most likely positive value of delta S, we want this delta S of hydration to be as small as possible, which means we want the smallest charge density possible. So if we want a small charge density, we want something that's got very low charge and something that's got very big size. So I don't remember the whole list, but I know there's some +1 ions and some +2 ions, some -1 ions and some -2 ions. We definitely want to pick from the plus one minus one list. And then we're going to use our periodic trends, which is another thing we should know from 124, right? We want to use our periodic trends to find the biggest radiuses possible to end up with the smallest charge densities possible. Does that make sense?
Do you know if there's any lab pal practice with charge density stuff? Because I don't think any lab pals have done it.
These problems are the practice with charge density. So
it's
it's like this indirect,
okay.
is this indirect practice with charge density,
Okay.
where you kind of are saying, how does charge density affect delta S, delta H? Delta S of lattice, delta S of hydration, delta H of lattice, delta H of hydration.
Okay.
So it's this kind of indirect thing. I know that's probably not a satisfying answer, is it? What kind of practice were you looking for with charge density?
Well, I just feel like we kind of like talked about it in class like a little bit, and then like it wasn't on really related to any of the lab pal questions, I guess, except these two. So then like I guess they kind of like left my mind because we didn't really do much work
it
with
was related to some problems on 2.2 as well when we were doing the delta H stuff, right? And the solutions lab, part 1 of the solutions lab, the solubility of ionic compounds, that also had charge density in it. Remember that whole grid we made?
Oh yeah.
That's all charge density.
The one with the
different colors where some things formed solids and some things didn't.
Oh right.
The whole argument for what's going on there is charge density. So that lab should have also had some charge density practice. The place where it's difficult is charge density doesn't often give us very definitive answers. It gives us comparative answers, right? If I just said, like in this problem, if we just said, does lithium chloride have a positive delta S or a negative delta S, you can't tell. But when I've got this long list and I say, which one's likely to be the biggest positive, I can compare the other things on the list and use it in a comparative way.
And it's the one that has like a bigger radius, but...
So, charge density is made of two things.
I just like forgot. I haven't done it in a while.
What does the word density make you think of?
Fast.
Oh, okay, good. What units does it make you think of?
Mass over volume?
Yeah. So if we want to do charge density, it's just charge over volume.
Okay.
And we get to our periodic trends by saying radius is 4/3 pi r cubed. And so we're just doing charge over radius, because 4/3 pi is all constant.
Okay.
So we're just looking at charge over radius to get us a general idea of the charge density.
Okay.
Cool. Other questions?
For the thing tomorrow or Wednesday, is it gonna be like how the quizzes are formatted?
Yeah, online portion of the exam is just essentially like
A
a big quiz.
Okay, and is there a certain time we have to take it, or just
Same
anywhere
thing,
from
6 to
8
midnight.
Or 6 to midnight?
Do you know how
6
many
to midnight.
questions are going
No, I have to make it as soon as you all leave.
to
I have an idea. I think it's 6 questions, but I have to double check.
And then
It's
for the midterm,
6-ish.
is the midterm gonna be like all class, or are we gonna have lecture in the midterm or something?
So I'll lecture for, no, I'm kidding. I'll lecture for an hour and then we'll take the midterm. No, I'm kidding. I'm designing the midterm to take 3 hours. No, I'm kidding. The midterm will take about an hour and a half and then I'll lecture. No, I'm kidding. It's just, it's sorry. It's literally, we're gonna do the midterm. I'm gonna sacrifice the hour. We would have an extra hour. I'm gonna sacrifice that hour because I don't think, I've tried in the past, lecturing after an exam doesn't help. Lecturing before an exam doesn't help. And 3-hour exams don't help.
Yeah.
So I'm planning on the exam only taking 90 minutes, but we'll have 2 hours. And then the last hour, leave.
Okay.
And what's going to be the difference between like the online midterm versus the in-person?
So the online midterm is essentially going to be like a quiz, right? A lot of calculational problems. LabPal does the calculational problems really well. A couple multiple choice questions, like those radial pick buttons. The in-person portion, this is also something we'll talk about in class tomorrow. The in-person portion is going to have 3 different parts to it: short multiple choice, long multiple choice, free response. Short multiple choice is like, do you know these key terms and definitions and ideas? You kind of like know them or you don't. They're worth like a point or 2 each. The long multiple choice is, can you read this problem, do these calculations, and get one of these 4 answers? Because only one of the 4 is right. So it's calculational things. Takes a little bit more time, worth like 3 to 5 points each. Then the free response is, can you do this calculation? Can you explain what you just did? Can you do another calculation? Can you explain what you just did?
So would you recommend going through the labs more for the in-person midterm?
I find the labs are a great way to prepare for the free response questions. They're not the only way. I find the next best way is to write problems for each other. People always ask me what's on the exam, and I'm like, you could probably guess. Like, if you had to guess, what would you guess is going to be on the exam? Pick like 3, each person, pick a problem you think is going to be on the exam.
Like an ice melting.
Ice melting problem. Yeah, there's probably going to be an ice melting problem. What's another one that could be on the exam? There's probably going to be something with entropy, right? What else?
The positive, negative, unknown.
Positive, negative, unknown. That would be a great problem to put on the exam.
Like question 3 from the colligative lab that we just did.
Question 3, right? Calculate the TIF, KF stuff. Yeah, that'd be great. I gotta make sure I do have that.
Oh, you don't have to put that.
Well, like this, I like.
To put an exam.
What else?
I was gonna say like, there's something of like predicting if a molecule dissolves in water based on.
Yeah, like the IMFs, whether it will be soluble or insoluble. Great, right? We can predict. Like, y'all just wrote a great exam. Or we could keep going. What else?
Is osmotic pressure going to be on there?
No, we didn't get the osmotic pressure, really.
I don't think that's.
No. Maybe you should. No, I'm kidding. It won't be osmotic.
Wave functions.
No, we're not. That's the wrong class. Can you think of another
I
problem?
was going to think of like the heater reaction.
Delta agent reaction. How did nobody said a delta agent reaction problem? Delta agent reaction would be a
Hess's
great
law
one. Ooh, Hess's law. That's another great one.
We're writing his exam for him.
Yeah, maybe I just leave right now.
So, but this is to get to the point of how do you prepare for the exam? Do this with each other. Do you have a study group? If not, you all should just make a study group right now. You all came to office hours. That shows initiative. That shows like desire to do well, desire to understand. So you all would make a great study group because you're probably going to encourage each other to do better. Now, for the free response part, so you can write these problems, you can find problems like online, you can find problems in LabPal, you can find problems in the textbook, practice all the math. The thing that most people have a harder time studying for is the how do you explain it? Because it's really hard to do graded problems for that. Like, the little essay thing we did, that was me trying to get us to think about how do we write things. But you should do that with each other as well. Like, how do you explain it? Not just vocally. You want to practice in the form of the exam. The exam is a closed book, closed note, written exam. So you don't want to just practice saying it out loud. You want to practice writing the sentences. And like, then you want to have somebody else read it and be like, does this make sense? Do you know what I'm talking about? And they might read it and be like, I got no idea. That could be because your explanation was unclear. That could be because they lack the understanding. So then you have that option of talking it through and being like, well, this is what I was trying to say. And they might be like, oh, try wording it this way then. Right? That practice of closed book, closed note, written, timed. Right? Give yourself time limits when you're practicing. I think 2 hours will be plenty of time. I don't think it'll be like a real time crunch. But we want to practice in that form of the examination. So practice writing explanations. Yeah?
So are the free responses going to be similar to the in-person, or the in-class?
Like writing thing?
Yeah.
Yeah. So my free responses usually have 3 to 5 parts to them depending on the question, but it's usually like do a calculation, explain the calculation, do a further calculation, explain that next part of the calculation. And so it's not just like do the numbers, lots of partial credit, like, you know, partial credit just for setting up the problems correctly, setting up the calculations correctly and stuff like that. But then you have that opportunity of like explaining what you were trying to do and getting credit for that as well. And that would be, that's what I recommend for the best way to study, is to actually just like write an exam and then like do the problems, and then also don't just do the problems and get the right numbers, but can I explain what's going on behind the math? Can I explain the chemistry of it? We're not just in a math class with word problems, right? We want to be able to explain those things.
Do you have more examples of like the things that we did in class? Like the writing things?
No, I've got to make some. So I have a lot for Chem 124. I only started doing those since the pandemic because I saw some writing deficiencies, some scientific writing deficiencies in students after the pandemic. I've only taught 125 once since the pandemic. So I'm trying to make more for this class. And I'm developing like, I specifically, I'm going to stop recording. This doesn't need to be on the video.